Okay, now we proceed with damped free vibration. So this time, the vibration comes with damping. So damping is analogous to friction, no? Katong sa ato ang physics. So maro ni siyang friction but for the spring. Okay, so before since ang ato ang sa atong drawing we have this kani, no? K, the spring has a K, which is a stiffness or spring constant, a mass, a particular velocity opposite to the kining or a particular force opposite to the displacement. And then this time naa na tay gitawag nga damping coefficient or kaning damper. So kung makakita mo ng grabe tong portahan nga naitaod sa ibabaw, nga dili mo lamba, so that is damper. So ang iyang concept ana kani, no? In this model it shows a spring and a damper all together tied a mass. Okay, so mo ni iyang pagmodel, and the forces acting on this mass is duha na, no? Aside from the spring force, we have what we call the damping force. Okay, so applying Newton's second law of motion, where the net force acting on a body is equal to mass times acceleration. So the net force here, duha na kabuok, we have the same principle, which is ang force is negative to or always opposes to the direction of the velocity ang damping force kani. So mura sa check sa spring. Okay, and then negative gihapon. So we have negative BV minus kx, which is Hooke's law, for the spring is equal to mass times acceleration, where our A is the derivative of velocity. Now sa kaning equation, we need to express this in terms of x or we rewrite this in terms of x so we can find the differential equation. Kay dili man pwede nga lain-lain. We have v, we have x, and we have a. Now we know that v is the first derivative of the x, which is the displacement, and a is the first derivative of velocity or second derivative of displacement. So we can express all these in terms of x. Now then we can rewrite the equation in standard form lang. We have then mapositive na siya. We move both to the other side, mapositive na siya. And then in standard form, the highest order sa pinaka left, we have the acceleration. So this is the acceleration, this is the velocity, and this is the displacement. So in this manner, ato nahimo ang ato ang homogeneous LCCDE. So if you notice, the response of the system then now vary depending on the value of m, damping coefficient, and the stiffness of the spring. Okay? So, muna yung timanaan in damped free vibration. Naka-free vibration siya because there are no external forces yet acting on this body. Sila lang sa, meaning sa circuit pa ni siya, this is still in transient response. Okay, so here, we rewrite this equation, our HLCCDE. We need to find the iyahang auxiliary equation. So, for the auxiliary equation, sa kini nga case, again, has 3 cases. So, quadratic man gud atong equation, no? If we generate the auxiliary equation ani, this is quadratic. Unlike sa undamped free vibration, ang ato is we only have m double x double dot plus kx. So mas kuan siya mas easier. Here namang gutay b, we have the first derivative. Now sa iyang auxiliary equation again has 3 cases which depends on the values of b, m, and k. So mao naman ni imong makam up, no? We have this b squared minus 4mk. So if at b squared greater than 4mk, our state is overdamped. B squared equal to 4mk, that is critically damped, and B squared is less than 4 mk that is under damp. Okay, so muna ato ang timan-an. So if we compare also kaning ato ang equation, this standard equation or equation come up based on the figure ani kaning model compared to the standard form of or general form the second order, which is kani, we can also see specific nga mga formula, no? Kung kani siya, we divide this with m, and m, k over m is actually equal to omega squared, omega naught squared. Okay, I think it's in the other slide. Timan-an lang nato ni in the problem if it asks unsay state sa ato ang body or atong spring or the model. So we can say that based on this is overdamped, is critically damped, and overdamped or underdamped. Okay, so comparing the actual equation that we have kini or here to the general form, diba kanina nakuha man ni nato, no? So sakto ra siya. This one is equivalent to k over m. So the angular frequency is equal to square root of k over m, that is in radians per second. And then from this here, kani, 2 zeta omega naught is equal to b over m. So we can generate that from this one, makakam up ta og zeta or the damping ratio. Okay, muna itong damping ratio equal to b, which is the damping coefficient over 2m times omega naught, where our omega naught is equal to square root of k over m, or our zeta or damping ratio is equal to b over square root of mk. Now, this damping ratio is, or depending on the value of the damping ratio, we can classify the transient response, which is katong kaganina b base atong b squared compare na to sa 4mk. Now, if zeta is greater than 1, our state is overdamped. Zeta is equal to 1, that's critically damped. If zeta is greater than 0 but less than 1, that's underdamped. And then zeta equal to 0 is undamped. Mo ni siya katong free undamped free vibration. So wala tay zeta dito. Diri ra na siya magawas sa kaning equation because there is the what we call the damper. Okay, so ato lang ning timan-an. We always remember this because usually sa problem it will ask what is the state depending on the damping ratio, what is the angular frequency, remember the standard form, and then the DE come up nga imong na generate or na formulate based on the problem. So mo lang na siya basically ang inyong things that you need to remember. Proceed with the example. Now, in the example, it says a 10 kilogram structure can be modeled with a mass. So we have this M structure, M equal to 10 kilograms. Then we have stiffness of the spring, that is K, equal to 290 Newton per meter. We have initially the object is pushed downward with a displacement of 0.1 or 10 cm, that is 0.1 meter initially. So that's the displacement, no? Initial displacement, that's 0.1 meter. And then we have release from this while in motion. The mass is subjected to a damping with a damping constant of 40 kilograms per second. So iyang B is 40 kilograms per second. So we have M, K, and B. Now, first question is determine the type of damping that the structure exhibit. So unsa iyang gid exhibit? Unsa to nga state? Okay, so using the formula or the comparison sa B squared sa over B squared sa 4mk, our B squared here is 40 squared. And then our 4mk, 4 times M is 10. So remember the SI unit na to, it should be the same sa tanan, no? Synchronous tanan. 290. Tama ba ko? 4mk. So pila man ni siya? This is equal to 1/6, which is this one is 1/600, meaning b squared is less than 4mk. It means that our the type of damping here is under damp. So under damp. So mo na yung answer ani. Okay? So yun na. Then calculate the natural frequency. So natural frequency. First, we need to find the hold on, the damping ratio. Sige, natural frequency lang sa ta. So the formula of our natural frequency is equal to 1/2 pi square root of k over m, diba? And so we have equal to square root of 290 over 10. So pila man ni siya. So use your calculator. The natural frequency is equal to 0.857 hertz. So muna siya sa letter B. Letter B, letter A. Okay, next is damping ratio. Now, the damping ratio, what's yung formula sa itong damping ratio? That is zeta equal to B over 2 square root of M times K equal to 40 times 2 square root of 10 times 290. This is equal to 0.37. So you can use your calculator para ma-confirm gid ninyo. So both are the answer for letter B. Okay, now third is find the equation that describe the motion. So muna ni siya pangitaon na to ang general solution. Okay, so we have the generated na tong equation in this damped free vibration, diba? The form is m x double dot plus b x dot plus k x equal to 0. Okay, and so we divide na to ni sa tanan sa m. We will have x double dot plus b over m x dot plus k over m x equal to 0. So b over m, that is 40 over 10, that's 4, meaning this becomes we can substitute now the values given sa b, m, and k. So we have x double dot plus b over m, that is 40 over 10, that's 4, x dot, no? Plus k over m, that's 290 over m, that is 10, that's equal to 29. X equal to 0. So naanatay DE. Okay, naanatay DE. Then we proceed with finding the general solution. What we do first is to find the auxiliary equation. So pulihan na to ni siya og m. Di na tama di agi og differential operator. M squared plus 4m plus 29 equal to 0 factor. Then the value of our m is actually equal to the perfect square. This is negative 2 plus minus 5i. Okay, so meaning our m is an exponential and a sinusoid. Duha ka buok. Okay, then we use the our x of t now is equal to this one. Kani siya mahimo na ni siyang hold on ha. From this one, ang formula na standard dapat ani is e to the 80. So this is our a and this is our b, no? So this becomes e to the 80 negative 2t times c1. Remember the standard form of kining general solution if our roots are in ani, no? C1 cosine 5t plus sine C2 sine 5t. So this is our general solution. Yan. So from actually this is a letter C, no, find the equation to describe the motion of the structure. So mo ni siya. So then we're looking for the position of mass at any given time. Okay, so we need to find the value of C1 and C2 first. Kay di man to ma-generate nga to ang position of the mass at any given time. Now, from this general solution, we need to derive this first before na to ma-substitute nga to ang initial value. Okay, so we have initial value of x0, x at 0.1 at t equal to 0. Then here our velocity is also at equal to 0, no? Initial condition. Now, before ta mag-derive, we derive first v of t. This is equal to e negative. But the final answer here, we can imura man siyang i-derive. The v of t here is equal to, just directly I will answer, no? E negative 2t times negative 5 C1 cosine 5t plus 5 cosine 5t minus 2e to the negative 2t times C1 cosine 5t plus C2 sine 5t. So this is product man kay times man ni silang duha, no? So the first was derive ni siya una times this, then derive e to the negative 2t times this one. Okay, so that's v of t. And then we can substitute the initial conditions. x0 equal to 0.1, and here, no, diri at the substitute. Then we have then actually we will come up with value of C1 is equal to 0.1 negative, and then C2 equal to, sige, hold on ha, we will write the actual equation now, substituting them with 0. Now for x, we have 0.1 ang atong displacement kanino, equal to e to the 0 times C1 times 1 plus C2 times 0. So we will have C1 is equal to 0.1. Then for v of t, we substitute 0, 0 kani. Then you will have 0 equal to 5 C2 minus 2 C1 is 0.1. Then our C2 is actually 0.404 negative. Okay, C1 and C2. Okay ba? Are we on the same track? So balik na ha from here. So first two, we have the natural frequency. First is the damping, so we can just compare kani, no? damping state or type of damping that the structure exhibit. Second is natural frequency. We use the formula. So, ayun ra kayo. You're good with substituting using the formula. Okay? And here, muli yung pinaka-tricky, which is using the differential equation that represents this scenario. Then we compare and or simplify and rewrite it in the standard form sa atong DE, so we can find the auxiliary equation. This is the auxiliary equation. Then our roots is this one. So the equivalent general solution sa ani is e to the 80 times c1 cosine bt plus c2 sine bt, where our b is 5, our a is 2. So before we can we need to find the value of c1 and c2. That's why we can use the initial condition. So before we substitute it in the initial condition, we have to derive x of t to find v of t. Kay our initial condition is natay x and v. Why? Sad nga no? Because we have two arbitrary constants to find. That is why dapat duha sa nga tuang equation. Okay? So after that, we were able to find c1 and c2. Muna ni siya. And then our x of t now, or the new x of t. Hold on ha. I'll add a slide. So x of t, mag-una ni siya no, nakukuha na tag value of c1 and c2. This is now equal to negative e to the negative 2t times 0.1 cosine 5t plus 0.04 sine 5t. So this is the response of the system. Okay, what is the amplitude? A is equal to the square root of 0.1 squared plus 0.04 squared, which is equal to 0.11. Then our phase is equal to tangent inverse of 0.04 over 0.1, which is equal to angle 0.38. So another form sa itong x of t is equal to negative 0.11 times e to the negative 2t. Nani na siya pagsulat sa final nga answer. Cosine 5t minus 0.38. Ito pa ngayon sa letter D. Position of the mass at any given time. Okay? So, mingon siya after 2 seconds. Sa letter E, what is x of t at t equal to 2 seconds. So, substitute lang na to. Velocity ani is at t equal to 2 is actually equal to 1.94 meters. No, substitute lang ninyo diri. Then the velocity is equal to negative 5.78 times 10 to the negative 3 meters per second. So ang direction downward, ngano man tungod sa negative. Okay, you try again the problem so para maka-answer mo ani, but the actual figures here muna siya after I calculated. You can use a calculator. Okay, so we now proceed with the second example for damped free vibration. Now a ball is having a weight of 98 newtons. Having a weight of 98 newtons is connected to a vertically mounted spring. So basically mo siya inani no. There is this force equal to 98 newton, and then which caused the spring to be stretched at by 1.09 m. So x is equal to 1.09 m, and then the ball is pulled downward by 0.016. So at x 0.16 meter siya released from the rest. So muna siya, and then siya describe the motion of the spring system if the damping ratio constant is 100 kilograms per second. So our B here is 100 kilograms per second. So we need to have the B, M, and K. So wala man tayo M and K, we need to find it first. We have this force here. So we can equate it with the mass, which is mg. So we can have 98 divided by gravity, that's 9.8. M is equal to 10 kilograms. And then our K is F is equal to Kx. Now, di lang tama apply sa sign because we're particular now with the kanang figure na, no, to find K. So we have 98 divided by 1.09. K is equal to 89.91. Okay, so we have K, M, and B. So before we look for the general solution or the DE based sa problem, we need to find the damping ratio first. So for us to understand the state, no, it's not intended, it's not one here, but we can describe it, no, describe man natong istorya. So una, look at the damping ratio with the equation equal to B over 2 square root of mk, which is equal to 100 over 2 times square root of 10 times 89.91. This is equal to 1.67. Now the damping ratio is greater than 1, meaning the system has an overdamped response. Overdamped response. Okay, isa na siya sa mga description based on the damping ratio. Now we proceed with katong say in the standard form for damp-free vibration. This becomes m x double dot plus b x dot plus kx equal to 0, right? Then we have the value of m. We substitute it na, so we can have the DE. M is equal to 10 times x double dot plus b is 100, x dot plus k is 89.91, x equal to 0. Okay, so for its roots, no, we need to find the auxiliary equation, or this is the find the roots. Use calculator. You can directly input it in the calculator para dili na kay complicated itong life. And so our roots is actually equal to approximately 1 is the negative 0.98 something, so that's negative 1. Then we have the approximate m2 equal to negative 9. Okay, and then we now have the general solution, x t c1 e to the negative t plus c2 e to the negative 9t. Now we have the initial condition kani, and then at velocity 0 at time equal to 0. So since we have two unknowns, dapat to sa dato equation, that is to find c1 and c2. Then we have the derivative of x of t. We have negative c1 e to the negative t minus 9 c2 e to the negative 9t. Here we can substitute x equal to 0. X at, sorry, we have initial condition 1.09. X equal to 0.16, the displacement. This is 0.16 meters at rest. T equal to 0. Here, 0 velocity, t equal to 0. Then we can have like c is actually, c1 is equal to negative 0.18, c2 is equal to 0.02. So the system response then becomes x of t equal to negative 0.18 e to the negative t plus 0.02 e to the negative 9t. Yan. That's it. Mura man niyang gipangayo. So this is the motion or the position